Last time we talked about multivariable integration. So here's one. Integral from 0 to 1, integral from 0 to 1, 4x squared over 1 plus x squared y, all quantity squared dx dy equals, we have numbers. Now we should get a number out. We're finding a total, so it should be a number. It's not going to be a function. You had a few minutes to look at this. Do we have an answer? Do we have a guess? A? Is that a guess or an answer? Answer? I think you're right, but I can't remember. All right, so we'll mark a tentative A. All right. All right. Well, let's find out. Let's find out. Now, normally when you see this, you have to remember how do we do integration, is that we would do it one layer at a time. And you're like, how would we do that integral? Well, I will note it can be done. I won't go through it. This is, if you did the inner layer, this is what would come out. So you have the technology to do it, but you don't want to do that. We still can get the answer, so don't worry. We're not done yet. We're not done yet. Let's think about what's going on. And here, there's sort of a nice idea. You ask yourself the question, would I rather? And now, what's the would I rather? Would I rather integrate with respect to x or y? So when faced with an integral, we ask ourselves this question. It's a big question. So look at this integral. So don't worry about the bounds. Look at the integral. You have a 4x squared over 1 plus x squared y quantity squared. Would you rather integrate this with respect to x or with respect to y? Well, the reason I'm asking, no, come on, we won't do that. We won't play that game this time. So, yes, y is the variable we'd like to integrate with respect to. How come? How come we would rather integrate with respect to y? What is it about this expression that makes y look more enticing? Sorry, what? There's only one of them, right? That's better. That makes things simpler. So we say, we would rather integrate with respect to y. So we say, okay, that's cool, but currently, what are we integrating with respect to? X. Well, can we change that? And the answer is yes. If we think about the region we're integrating over, we say x, read off the bounds, where does x go from? 0 to 1. So those are our x bounds. Where does y go from? 0 to 1. So our region is this square from 0 to 1. So what we'll do is we'll say, okay, we'll do the same integral over the same region. So we're not changing the function, we're not changing the region, but we're going to change the order that we integrate. So you can think of what's happening now is because we're integrating the outer layer is dy, and then the inner layer is dx, you say fix a y value and then go along x. So it's like we're slicing in this fashion. Because iterated integration is about slicing. What are we going to do? We're going to change it so we slice in this fashion. All right, so we're going to think about, we're going to do an integral again. Same function. That hasn't changed, but change the order. Now, previously, x went from 0 to 1. But now, where will x go from? Yeah, it'll go from 0 to 1. And previously, y went from 0 to 1, but now where does y go from? Yeah. This is called, you're a rectangle. When you're a rectangle, it's easy to switch the order of integration. When you're not a rectangle, stay tuned. We're going to get there in a couple minutes. It's a fun story. All right, so now we have the same integral. So whatever comes out of this will be the same answer. Well, let's make it more calculus friendly to actually do the integral. Integral 0 to 1, integral 0 to 1, 4x squared, 1 plus x squared y to the minus 2 dy dx. All right, so how do we integrate it? So don't think of it as two integrals, just think of it one integral at a time. We're peeling away. If you saw this integral, we treat x like a number, what would you do? What would you do? You can pull out a 4. You can even pull out the x squared. But again, how would you integrate this with respect to y? Because there's only one y. That was our like why we like to integrate with respect to y. What can we do to integrate this? Any ideas? Substitution. Okay, substitution works great. I love it. Okay, good. Where should we substitute?
1 x squared and 1 plus x squared y.
We'll just do the whole inside, right? U equals 1 plus x squared y. Now remember, at this stage, we are thinking of x as a constant. Only the y is the variable. So what is du? X squared dy. Oh, there's an x squared dy. How convenient. Almost as if it was planned, because it was planned. Okay, so we still have the outer layer. We'll get there. Don't worry. Don't worry about that. We're working on our inner layer. It's now going to become a du integral. Okay, so the x squared dy becomes du. We still have a 4 for some reason. What will this 1 plus x squared y to the negative 2 become? U to the negative 2. What will our bounds become? Currently they're 0 and 1. And remember, these are y equals 0, y equals 1. What will our new bounds become? Plug in 0, you get 1. Plug in 1, one plus x squared, right? Because it's 1 plus x squared times 1. Yes? So far we're good? All right. You got to know where we're going, all right? You can probably sense it. It's like, oh, I know where Steve's going with this. I can feel it. Can you sense it? Where are we going to end up here? Yeah, there's an arc tangent in our future. It's like, okay, Steve wrote this one. I did. I wrote this one. All right, what's the integral of u to the negative 2? You add 1 to the exponent. U to the negative 1. What else do you need to do? Divide by that new exponent. So we'll have negative 4 u to negative 1, which we can write as negative 4 over u. Evaluate that from 1 to 1 plus x squared dx. So we have, when we plug in the 1 plus x squared, we have negative 4 over 1 plus x squared. Subtract negative 4 over 1, so minus a minus 4 makes a plus 4. All right, now this seems a little bit easier than the integral we saw a few minutes ago when we had to integrate with respect to x. What's the integral of the first term? What? The negative 4 is a constant. Integral of 1 over 1 plus x squared. Arctangent! It's an arctangent. Steve taught the semester. What's the integral of 4? 4x. And now plug in from 0 to 1. Well, that's minus 4 arctangent of 1 plus 4 times 1 minus 0 Arctangent of 0 is 0. 4 times 0 is 0. Do we know what arctangent of 1 is? We do, yes. Can anyone tell me the exact number? Pi over 4. So that's the 4. 4 times pi fourths ends up with pi, so don't forget the minus, so it's minus pi plus 4. So A is indeed the correct answer. Nice! All right, good. Any questions? Could you do it? Well, don't worry. That test is in a few weeks. That's not till like December. So you don't have to do it today. But we'll need practice, right? We want to get to the point where we're comfortable doing these types of problems. So, thought for today from a story by Hayao Miyazaki, who wrote Kiki's Delivery Service, I believe is the name. And this is a quote. First, don't panic. Second, don't panic. And third, did I mention not to panic? And I think this is partly in response to the fact that we have an exam coming up. Don't panic. That's not going to help you. Put in the time and the energy. You got to this point. You got to calculus 3. You know calculus 1. You know how to do these integrals. You might be a little bit rusty. That's why we're going to be practicing. Just think about it. We're not going to give you something you can't do. We'll give you problems that you're capable of. Now, what's our goals for today? We're going to talk about integration over non-rectangular regions. So last time we talked about integration over rectangular regions. We're still doing iterated integration. That's what we're doing for the next couple of weeks, iterated integration. So most of our conversations are going to center around how do we set things up. And the key here is going to be describing the regions. And we're going to talk about changing the order of integration. And so the moral is the bounds secretly hold a description of the region. Now what we can do is we can change the description of the region. That's this little arrow here. And by changing the description of the region, we can change the bounds in the sense of changing the way we describe things, which comes with changing the order of integration. So this idea of from the bounds, we know what the region looks like. We change the way we describe the region, which gives us our new bounds. So that's what we're going to be doing. And we'll do it multiple times. We'll do it in different coordinate systems, and we'll do it in multiple dimensions, not just dimension 2, but also dimension 3. Oh. All right. Before we do that, there was one slide I couldn't finish from last time. So there's a useful fact that I will from time to time pull out, and I just want to explain why it works. And this is for integration over rectangular regions. So if you're integrating over a rectangle, so x goes A to B, y goes from C to D. So right, you need your region to be a rectangle. If it's not a rectangle, you can't use what we're about to do. And your function is special in the sense that you can write it as a function of x times a function of y. So if both those things are true, you're integrating over a nice region, rectangle region, your function is nice in that you can sort of pull it apart. Then the punchline is you can do your integrals, instead of 2 iterated integrals, it's the product of 2 single integrals. Why does it work? Well, start with the inner layer. You're integrating with respect to y. So how do we treat g of x? It's a constant. So the punchline is, since g of x is constant, you can pull constants out of integrals. So that's what this is indicating. Pull out your constants. So here's your g of x been pulled out. Now, when you actually integrate this, what comes out at the end? Well, it says it right there. It's a constant. So if this is a constant, what can you do with a constant inside of an integral? pull it out. That's separation. So it's just a matter of like, oh, I can pull constants out. And so this can sometimes say, look, instead of trying to do one layer at a time, I say, oh, I'm over a nice rectangle, I'll split it and just do them all simultaneously. So that's the idea. All right. Well, let's start by talking about integrating over a region which is not a rectangle. But we still have our same basic idea. We have our region, we'll stay in the xy plane. And over it, there's some function z equals f of xy. So there's this surface floating upstairs. And so we can ask, what's the total? So we can think about this, there's this solid being formed here. What's the total amount? And we say, well, how do we approach it? And the answer is we do what we did before. We're going to slice and dice. So what can we do? Well, so here's our region R. So this is our same region here. So this is R and this is R. I'm just looking at it, and I'm going to ask, how can I slice it up? Well, there's two ways to do it. One way, which is doing this here, that's where we're slicing what I like to call vertically. So we're slicing our region up, and we're going to go from the top to bottom. And so we need a way to describe things. So x goes from A to B. There's a curve on the bottom, which I'm calling phi1 of x, and there's a curve on the top, which I'm calling phi2 of x. And now, what's the total? Well, like last time, we add up the contributions of each slice. So there's an integral. But what's the contribution of the slice? Well, what we do is say, what do our bounds are? Or, what do our bounds go between? We're integrating with respect to y, because we're changing y. We say, well, we go from the bottom to the top, right? Or if you like, top minus bottom. And so that's why you see these functions, phi1 of x, phi2 of x. Now, that's one option. There's a second option, which is we can slice in a different way. So we can slice this way. And that's what's being shown here. So we're slicing our region horizontally. So now the y value is going from some minimal point C to some maximal point D. And now what's happening in each individual slice? Well, there's a contribution being made. So you say, what's that contribution? Well, you go from left to right. Low value, high value. So just whenever you're wondering like which order you put the curves in, low to high. And so we say the outer layer, we integrate from C to D for y. And then for a fixed y, so we fix our y, we go from left to right. Psi 1 of y, that's the curve on the left, to psi 2 of y, that's the curve on the right. Now, a few things that we can say here. Initially, let's think about what happens. If I just look at this piece right here, what do I have? Well, I have a function of two variables. Okay, so I see two things which vary, x and y. If I go another layer and I integrate, what will I have here? So I've carried out the integral. What will happen? What will I have? So on the innermost layer, we see both x and y. When we do our first layer, which includes doing the integral, carrying out the evaluations, what will we see? Yeah, here we're only going to see x. But what happened to the y? Well, we integrated it out. Because once you've integrated and then you evaluate, because you're going to replace all the y's by expressions involving just x. So after one layer, you've knocked out a variable. So by the time you hit the middle layer, we'll be down to a single variable. If we finish it up, go all the way, what will we have at the end? We'll get a number out. So initially we start with a function. Once we do our first integral, we lose a variable. Get down to a variable of just a function of a single variable. Integrate again, we'll get down to a number. It's the same thing that's happening over here. All right, so let's just do one. We won't worry about how to set it up right now. That's coming in a minute. Let's just do an integral. Find the integral from 0 to 1, integral x squared to x, of 12x plus 15y. Now, if we channel our, which way should we integrate with respect to, we come to the conclusion, these both look fine. Okay, so remember, we do this one layer at a time. Start with the inner layer. What are we integrating with respect to? Y. Yes. It says it right there. It's like we're giving clues. We want you to know things. So, if we're integrating with respect to y, how do we treat this x? Constant. All right. Now, another thing to note is that these boundaries are bounds for the integral. These are really y bounds. So this is y equals x squared, y equals x. Okay, so when we start peeling away, we'll see what we get. What's the integral of 12x with respect to y? 12xy. What's the integral of 15y with respect to y? 15y squared over 2, or 15 halves y squared. Now, we're going to evaluate this, and then we're going to do our next layer. So we have to complete the whole process before we go to our next integral. So we're evaluating y equals x squared, y equals x. I like to put the y equals just to help me remember what am I plugging in. Because sometimes it can be easy to forget, especially once we get to triple integrals, which we've mentioned, triple integrals are coming. All right, well, we plug in x. So everywhere where we see a y, we put an x. What does that give us?
X.
12 times x, that's 12x squared, plus 15 over 2 times x squared, 15 halves x squared. Okay, subtract. Now, everywhere where we see a y, put an x squared. 12 times x squared, x cubed. All right, x times x squared. 15 halves times x squared squared. Another way to say x squared squared, x to the fourth. Now, we are allowed to simplify. And generally, if you remember our conversation from before, you should simplify if it helps you. And if you're about to do an integral, simplifying will help you. Is there anything that will simplify? Well, these x squared should combine, right? Because they're both x squared. So we should just add their fractions. What's another way to say 12 in terms of halves? 24 over 2. So 24 over 2 plus 15 over 2 would give us a number. I think it's 39. Yeah, 39 over 2, and that's an x squared. And then the minus, we can go ahead and distribute that. Minus 12x cubed, minus 15 halves x fourth. There's nothing else we can combine. All right, now we're back to a Calc 1 problem. Woohoo! Calc 1, Calc 1. All right. So, what's the integral of 39 halves x squared? So it's 39 over 6 x cubed. Integral of 12x cubed. We can do 12 over 4 x to the fourth. So remember, the 4 will go downstairs. When you integrate, when you differentiate, it goes upstairs. Integration goes downstairs. Minus 15, and then you're going to have an x to the fifth, so you're going to put a 5 downstairs. There's already a 2 downstairs. So, and evaluate from 0 to 1. Now the good news is 0 and 1, they're some of our favorite numbers. So when you plug in 0, what happens when you plug in 0? 0, 0, 0. What happens when you plug in 1? Coefficients. So we end up with 39 over 6, minus 12 over 4, minus 15 over 10, and minus 0. But this would probably be a multiple choice problem. That wouldn't be an option because they'd actually have simplified it. Because I think we can simplify it. Is there another way we can write 39 over 6? 13 divided by 2, because there's a factor of 3. Another way to write 12 over 4, because 4 goes into 12. How about 15 over 10? Minus 3 halves. 13 halves minus 3 halves?
Can we change that 3 to a...
Would 10 halves? 10 halves, also known as 5. 5 minus 3? 2. So there's the answer, 2. Good times, good times. All right, so once you put in functions and bounds, same process. Nothing really changes. Just work on the inner part, integrate the inner part, plug in, integrate the next part, plug in, and you keep going. Now, we have an important statement. Notation is important, yes. We've mentioned this already. In Calc 1, you're like, do I really need to put the dx? And we're like, well, yeah, if you want 10 points. Otherwise, we'll take a point off. And we did that so that you would get into the habit of writing it down. Because you need it here. You need to know what you're integrating with respect to. And also, it helps you understand what the bounds are doing. So, if you switch the order, you switch the description, and you might be trying to integrate over the wrong thing. So the outer bounds go with the outer d part. So the outer bounds are always between two numbers. So a number to number. The inner bounds are going to be between two curves. So y equals phi1 of x to y equals phi2 of x. This was still true when we were doing rectangles. It just didn't seem obvious because of the way it ended up working out. But this is always the case. The outer layer goes between two numbers. Next up, we go between two curves. And in particular, we can read off the description of our region. We say, well, where is x going from? And it says, well, x goes from A to B. So A less than or equal to x, less than or equal to B. Where is y going from? Well, that's coming to here. Y goes from phi1 of x up to phi2 of x. So phi1 of x less than or equal to y, less than or equal to phi2 of x. All right, so here we have two integrals, two different integrals. And so let's see if we can sketch the regions that are associated with these integrals. So we're not worried about the function. We're not carrying out the integral. We're just trying to understand the region. So let's start with the first one. So first thing, let's start with the description. Where is x going from? 0 to 2. Where is y going from? 0 up to x squared. Now what we can do is we can say, all right, well, what does this tell us? Well, our x goes starting from 0 up to 2. So we have this place at 2. So that's the bounds for x. Now, in between, we see that we're going from y equals 0, which is this curve. So this is the y equals 0 curve. And then we're going to y equals x squared, which is part of a parabola. So here's y equals x squared. And in particular, the way we're thinking about this region is we're slicing, this is our vertical slicing, up and down. So we're having y go up and down as we go along x. So there's our region. All right, so it's not too bad. Not too bad. Any questions about this part? That seem okay? All right. Well, in that case, let's do the other part. So, different integral, right? The bounds are different. So, let's again work through it, one layer at a time. What can we say about the y? 0 less than or equal to y less than or equal to 4. What can we say about x? Square root of y less than or equal to x less than or equal to 2. It's in the bounds. Everything we need is stored in the bounds. Okay, so we'll sketch here. Now we're going to go from y. So y goes 0 up to 4. Okay, so we have 0, we have 4. Where does x go? Well, x equals 2. We know how to draw x equals 2, so that's not so bad. We have an x equals 2. What does x equals square root of y look like? Do we know what that looks like? It's what? Oh, it looks a lot like y equals x squared, yes? Yeah. So this is x equals square root of y. And now what's happening? Well, really, we're going along y, and as we fix a y, we're going from left to right. So we're slicing horizontally. Now, a moment of truth. As we stare at these pictures, do you notice anything? They're the same. Okay, good. All right. It wasn't too subtle. Good. Phew. Okay. Same picture. So what does that tell us about these two integrals? If we carried out these two integrals, what would be true? These two integrals are equal to each other. Because you're integrating the same function, you're integrating the same region. But now, you might say, but wait a second. This looks a lot different than that. Yes. When you're going over non-rectangular regions, the descriptions can change, and they can look not necessarily the same. So how do we do that? So that gets us to today's topic. In the last few minutes, we can actually talk about what our goal is today. So our goal, changing the order of integration. Now, I know there's a lot of words here, but it's actually a lot simpler than it seems. How do you change the order of integration? Well, first thing is, what's your region? And in particular, how do we describe our region? The bounds are storing the description of our region. So that's where we go. And I do apologize. When I say changing order of integration, essentially that means we want to go from dx to dy down to dy dx or vice versa. So we want to say, I want to change what I integrate with respect to first. That's what we mean by changing order of integration. So the bounds are storing the description. So we grab that description. Now that we have the description, draw a picture. Now, it can be helpful to indicate how to slice. It's not needed. Now you have a picture. You say, all right, I have a picture. I know which curves bound my region, and I label them. So each bounding curve should have a function attached to it. Sometimes they're simple like x equals something or y equals something, or you might get y equals x squared or x equals square root of y. It just depends. Once we have our bounds and we have our labels, we check to see if we need to break it up. Why do we need to break things up? Well, sometimes you have to break integrals into multiple parts because your description needs multiple parts. Something is changing in your bounding curve. And if you have a change in your bounding curve, you have to change the description. So that's a place where you say, let me break my integral into pieces. Now, for each part, find a new description. All right, so the process is fairly straightforward once you start doing a couple of them. So we'll have time to do at least one more before we finish today. Some comments. Sometimes you don't need to change the order of integration. Sometimes you just need to set up an integration. So just start at step 2. And always before you set up an integral problem, ask yourself the question, which thing would I like to integrate with respect to first? Sometimes it doesn't matter, but sometimes, like in our warm-up problem, it can matter a lot. So be careful. 0 is a friend. We like 0. 0 is a friend because it makes a lot of things go away. So if you can, pick a description with lots of zeros. The more zeros you have, the easier something tends to be. Be careful. Changing the order of integration might cause the number of parts to go up. It can also cause the number of parts to go down. And when I say the number of parts, maybe you started with one integral and say, oh, now I have to do 2 integrals. Or vice versa. Maybe you're starting with 2 integrals, now you have to do 1. And this last part probably is not a big surprise. If you change the order of integration, it can make some impossible integrals possible. So some things that are just like, we have no hope of integrating this. You say, well, you're looking at it wrong. Don't integrate with respect to x first, integrate with respect to y first. You say, well, that's an easy integral. But then once you carry out the evaluation, then all of a sudden something comes up, almost as if it was planned. And then it can actually be done. All right, so that's the procedure. Let's try a problem. Change the order of integration for the following. So notice we're integrating dx dy. And then we're switching to dy dx. So that's why we say we're changing the order of integration. And let's be clear what you don't do. What you don't do is just say, oh, I'll swap. And then I'll put a -1 to 0 here, and a minus square root of y plus 1 to square root of y plus 1 there. If you do that, you will lose lots of points. And we don't want to lose any points. We love all our points. They're all our precious. Are precious.
Okay, please calm down.
So, now, what can we do? Well, we start the process. So we start by saying, let's think about what our region is. So the region is being stored in our bounds, and remember how bounds connect to the variables. So, what can we say about y? Where does y go from? -1 up to 0. All right, now what can we say about x, the next layer? Where does x go from? Negative square root of y plus 1, less than or equal to x, less than or equal to square root y plus 1. It's in the bounds. All right, so let's draw our picture. Now, before we do that, if we see something like x equals square root of y plus 1, what's another way for us to think about this curve? Because that does not look like a curve that we might recognize off the top of our heads. Yeah, in fact, if we say plus or minus even, you square both sides, that's x squared equals y plus 1, or y equals x squared minus 1. So there's this curve, y equals x squared minus 1. It comes down. It does this. So this is y equals x squared minus 1. The left-hand side of this curve, over here, this left-hand side, this is the curve x equals minus square root of y plus 1. The right-hand side, that would be the curve x equals positive square root y plus 1. Can you see where negative 1 is in this picture? Or y equals negative 1. It's right here at the bottom. And y equals 0 is the axis. So we are doing this region here. This is our current way to approach it. Slicing horizontally. So it's the bottom of the bowl. All right. So we got the bounds. We rewrote the curves. Now, let's clean up our picture. What goes on? Well, instead of slicing our horizontal slices, we're going to slice vertically. So, what information do we need? Well, where do we hit on the x-axis? Do you see those values? Negative 1, positive 1. You know, when does x squared minus 1 equal 0? What's the curve on the bottom? That's the curve y equals x squared minus 1. What's the curve on the top? Y equals 0. So we can describe this region. Another perfectly valid way to describe this region is negative 1 less than or equal to x less than or equal to positive 1, going between two numbers for x. And then y is going to go from two curves. The top is the curve y equals 0, and the bottom is the curve y equals x squared minus 1. So our two descriptions are both ways to describe our region. We're just changing the way we're describing it. But now we make it friendly for us. So the outer layer, that's the x layer. What goes in our boxes? Negative 1 to 1. Number to number. The inner layer. Y, we're going from curve to curve. What goes in our boxes? X squared minus 1 to 0. Yes? All right. We have a few minutes. I think we can do one more. One last problem to finish it up before we take our break from integration. So, find the integral from 0 to 1, integral x to x to the 1/3, 24 square root of 1 minus y to the 4th dy dx. Now, our initial reaction. Do we want to integrate this with respect to y? No. Now, your other initial reaction is, I don't even want to integrate this at all. But that's not an option. You got to integrate. You say, but okay, would you want to integrate this with respect to x? Yes. What makes x better in terms of like integrating? There's no x. So all of it is constant. I like integrating constants. That's pretty easy. So, idea, if you see something like, I don't know how to integrate that, you say, but wait, if I change the order, I can at least do it once. So when you see like these ridiculous integrals, that's a clue. Change the order of integration. All right, so we're going to do a little bit of a speed run so we can try to finish on time. Our description, x goes from 0 to 1. No problem. Y, our inner layer, goes from curve to curve. Y equals x to the 1/3. Now, on a side note, you're taking the class in the semester when there's somebody who writes the exams. Well, there are several people who write the exams together, but one person knows how to draw pictures. And so we would give you a picture. So if you're kind of like, oh my gosh, what do these pictures look like? This is one I think we'd give you a picture on. But I think some of these curves we probably know. Y equals x looks like this. Y equals x to the 1/3 looks like this. And what's happening? Well, they intersect at a very convenient place, almost like we planned it, at 1. So we are currently, whoops, no, wait, I think I got this backwards. This was right. We're slicing this way. So x goes 0 to 1, and then we're going up from y equals x to y equals x to 1/3. So that's our shape. Now, what do you need to do? For every line, or every curve that bounds your region, switch it. Right now, it's y is a function of x. So I don't want y equals x. I want x equals something. If y equals x, what does x equal? Y. If y equals x to 1/3, what does x equal? Y cubed. And now we're ready to start talking about this kind of slicing. We have to find a couple of points. Which y value is this at? At this corner? 1 and 0. So we have 0 less than or equal to y less than or equal to 1. That's where y goes from. And then x, left to right, low to high. So what's on the left-hand side, the low value? Y cubed. Always think low to high, low to high, left to right, down to up. So we haven't done anything with the actual integral in terms of integration, but what we have done is we've changed the description. So we get 24 square root 1 minus y to the 4th dx dy. All right, so there's the new integral. Well, now we say that we can integrate with respect to x. As has been pointed out, hey, that's an easy integral with respect to x because there's no x's. So we just get an x for free, right? Constant x. Evaluate from x equals y cubed to x equals y. Equals the integral from 0 to 1, 24 square root 1 minus y to the 4th times y minus 24 square root of 1 minus y to the 4th, whoops, y 4th, y cubed. All right. Oh, we're out of time. Do you want me to finish up, or should I just leave it as a mystery and we'll never know? Finish it! Finish it! Okay. On a side note, this came from an old exam. An old exam. I know who wrote the problem. I did. I wrote this problem. How do you integrate this? Well, we're going to use the power of the minus sign here. And one of the things that it allows us to do is to break it up into two integrals. So 24y square root of y, 1 minus y to the 4th dy, minus integral 0 to 1, 24 square root of 1 minus y to the 4th, y cubed dy. Okay, can anybody tell me how to do one of these two integrals? If you do one of them, I'll tell you how to do the other one. What do you mean by 0? Neither of these integrals is 0.
U equals 1 minus y to the 4th for the right one.
Okay, so you chose the right. If you choose u equal 1 minus y to the 4th, du is minus 4y cubed dy. So, what does this integral become? Using our fancy extended paper technology, this integral, we have a minus, we have that 4. We can pull that, 24 is 6 times 4. So we're going to get a plus, because we've got the minus, 4y cubed leaves us with a 6 du u to the 1/2. Are in our bounds? Well, plug in 0. We get 1 up to 0. Okay, so this part, well, that's the same as minus 0 to 1, 6 u to the 1/2. Just change the order back. Flipping the order introduces a minus sign. And that is a straightforward one. Integral of u to the 1/2 will be u to the 3/2, and then times that by a 2/3. And you say, okay, well, 3 goes into 6, and you evaluate 0 to 1, we end up with minus 4. That's from the second integral. And I said, if you do one, I'll do the other. So here's the fun one. This is the one that people did not like. U equals y squared. What's du? 2y dy. So this becomes integral 0 to 1. 0 squared is 0, 1 squared is 1. 2 comes out, I'm going to think of this 24 as 12 times 2. So 2y dy becomes du. And I'll pull 12 out. And then we have square root 1 minus u squared. Do you recognize this? It's a quarter of a circle. 1/4 of a circle of radius 1. So, by geometry, it's 12 times pi fourths, which is 3 pi. So our final answer, 3 pi minus 4.